faculties, and participants. Let me introduce our today's expert. Dr. Asutosh K. Giri received his Bachelor of Engineering in Electrical Engineering from College of Technology, GB Pant University of Agriculture and Technology, Pantnagar, Uttarakhand, India in 2002. ME in Electrical Engineering with specialization in Power System from the LD College of Engineering, Ahmedabad, Gujarat, India in 2005, and PhD from the Department of Electrical Engineering, Sardar Vallabhbhai National Institute of Technology, Surat, India in 2002. He has authored and co-authored more than 40 research papers in reputed journals such as IEEE, Transactions, IET Journal, Wiley, Taylor Francis, Springer, etc. He has also co-authored one book chapter which is published in Springer Publications and edited two books for each of CRC Press, Florida and Springer Nature, Singapore. He is working on this 3 sponsored research project costing around 28 lakhs INR, Indian rupees. One sponsored research grant of rupees 25 lakhs from the Director of Technical Education, Gujarat State under STEM scheme is in a foreign university collaboration center of CROM University, Denmark. Currently, he is supervising 3 PhD students. He has conducted 5 STTP, including recently conducted Atal FDP at GEC Bharuch. He has delivered more than 25 national and international level expert talks at various reputed universities across India. He had received a Research Opportunity Week ROW scholarship and visited Technical University of Munich, Germany in March, April 2019. So we have very good expert with us. So I request all the participants be with us for next sessions and interact with our experts and solve all your questions. Thank you all participants. Thank you, sir. Mike, over to you, sir.
Thank you very much, madam, for introduction. Thank you very much for inviting me, for giving me this wonderful opportunity. And I am also very much thankful to you for taking a very nice initiative to organize such kind of programs, which are very much beneficial to the people who are working in this renewable energy sector and domain. And now I would like to share my slides first. Yes. अभी 1 घंटे के बाद now yesterday we were discussing about the classical controls and its limitations. Now today we will see some kind of controllers which are based on adaptive theory based controllers we will see today in this session, and we will also see some simulation results what we have performed. My PhD students are doing work on the solar wind microgrid system, and we will see some results in this session. Now I am sharing my slides. I think so screen is visible.
Yes, sir.
Okay. Let me share first. Yesterday we have covered various topologies and classical control algorithm. This algorithm we have covered till this one, and this classical control algorithm is based on basically transformation principle and 3-phase PLLs. Yesterday we have discussed what are the various limitations of 3-phase PLL and why these kind of classical control algorithms are becoming inefficient or obsolete if some fast dynamical changes in the system is occurring. Suppose if we take the system of wind and solar microgrid, then during the wind variation, because wind is totally unpredictable, you can predict solar intensity for certain hours, but wind is totally unpredictable. In these kind of systems, wind are changing very fast, rapidly, and your control system must be able to respond the fast changes which are occurring in the system. That means, because you see the input is wind for any wind generator, right? And if solar and wind, they are they are connected in parallel, and if one side is fluctuating, another side will also starts fluctuation, like DC link voltage starts fluctuation. Yesterday you have seen the DC link voltage and different topology. Suppose just I want to remind something for a few minutes. Suppose we are taking this example. This is very simple example of solar wind microgrid, right? Wind generator is connected here, and we are connecting wind generator at the DC link of the solar. DC link, at the same DC link, solar generator or solar generation and wind generation, both are connected, right? And through this inverter, we are giving supply to the grid or load, right? Load is here. We can supply grid or load through this topology. So what I mean, my point is, though solar variations are not there, suppose solar radiations are fixed for certain hours, but if wind is changing, entire system starts in fluctuation. That means voltage frequency, it will not be easy to maintain when certain parameters are changing either from the wind side or from the solar side. So these are the things which can be addressed by using some adequate, or you can say delicate, control mechanisms. And those control mechanisms are adaptive control mechanisms, and we can control the entire operation of this inverter. Suppose this inverter, if you want to control the voltage and frequency, ultimately you have to control the operation of the inverter, because the DC link fluctuation can be minimized with the help of the control of the inverter. Reactive power injection, or you can say real power control through this route, it can be controlled. Balancing can be obtained, harmonics can be minimized, right? All these things can be taken care by this VSI, voltage source inverter, just by some control algorithm. Because voltage source inverter is nothing but it is the combination of switches. 6 switches are connected at 3 legs, right? And with the help of certain sequence of certain gate patterns, that means gate pulses, we have to generate 6 gate pulses to fire these inverters in such a manner it will maintain the balancing of the power, or it will maintain very less harmonics from the grid supply. It will maintain almost sinusoidal supply from the grid side. That means we are firing the switches in such a manner, and from where we are firing the switches, from where we are generating the gate pulses, we are generating the gate pulses by using some control algorithm. Control algorithm may be running at the controller, may be running in the DSPs, but ultimately the output of the control algorithm will be the gate pulses. Now yesterday we have seen in our classical control methodology, just I want to connect previous lecture to this lecture. Just a minute. मैडम 1 बजे एग्जाम रखेंगे, ठीक है? हाँ, 1 बजे एग्जाम रखेंगे, 1 o'clock पे हम एग्जाम रखेंगे. लेकिन अभी क्या है कि मैं भी लेक्चर में था और अभी भी लेक्चर दी है, तो मीटिंग है, तो कोई बात नहीं, 12:30 को मीटिंग है, तो हो जाएगी. हम 1 बजे से करेंगे एग्जाम. अभी मैडम इज आल्सो बिजी. हाँ हाँ हाँ, ये स्टूडेंट्स आए तो उनको 1 बजे का बोल दें. हाँ, 1 बजे. ओके. Yes, now yesterday we are discussing about the controls, classical control mechanism, and now today we will discuss the adaptive control mechanism. There are 3 type of area where we can control the device. That is primary control, local area control. That means if we are maintaining something at the area wise, then secondary control, And if it is connected, your microgrid connection is connected from the grid, then we have to use some switch control that will be coming under the category of tertiary control. Because we are taking here only standalone systems, only device, one inverter or two inverters are used in our topology. Suppose you are using solar roof panels, then only one inverter is basically enough to supply energy from generated from the solar roof panel to your house. So one inverter is basically controlled by using primary control. It may be based on voltage reference or it may be based on current reference, right? So basically, whatever we are discussing here, that is the part of primary control. And this is the control algorithm. Yesterday we have discussed. Just I want to make you connect again from the previous lecture to this lecture. So this is the IL extraction technique, how we are generating the reference. Yesterday I told you about the gate pulses as generated from certain set of references, and these references are created from this control algorithm. So this is the control algorithm which is extracting the reference, desired reference. Suppose if we want to maintain, if your solar rooftop panels are grid connected, or if you want to maintain load supply as a sinusoidal supply, right? Or if you want to maintain load voltage constant, or if you want to maintain inverter harmonics level, that means should be less, inverter should supply a sinusoidal voltage, then you have to generate sinusoidal references, because whatever the references, entire operation will try to follow these references, right? That's why references are very much important. And unless and until yesterday some participant has asked very interesting question, how we can say the references are coming correct. Suppose you are using 10 ampere load current, references must be equals to the real component of the 10 ampere load current. It may be 7 ampere, 8 ampere, but it will never be 2 ampere or 1 ampere. If you are connecting 10 ampere load with active component only 2 ampere, that means your load power factor is very poor, and it is not, you can say, it should not be connected from any system, otherwise system efficiency will go very low. That's why you can see here the references are correct or not according to the load current measurement, right? And we are sensing, we are measuring the load currents at regular intervals, and we are generating the reference current. For any control, the inputs may be DC link voltage, load currents, and supply voltages. For any control, either it is classical control or adaptive control mechanism. Actually, when you are purchasing any inverter is inbuilt with certain control algorithms. That's why you are least bothered about the control mechanism. But if you want to make your own inverter, these things which you have to learn, you have to make your own inverter, you have to make your own controller, you have to make your own control algorithm. By this way, you have to see everything. If you are not purchasing, if you are making, right? So by this way, you are generating the gate pulses from this PWM controller, and these gate pulses will be given to the 6 switches of the inverter, which is used anywhere in the either it is wind connected system, or it is solar only, or it is the combination of wind and solar. If you are using a perfect topology, you have to generate the pulses, and accordingly objectives will be fulfilled. Now, yesterday I told you about the drawbacks of the PLL. Any control which is working based on the PLL principle, because PLL is giving some estimated sine theta, cosine theta to the transformation blocks, and if estimation is wrong due to imbalance in the voltages or distortion in the voltages, this cos theta, sine theta estimation may be wrong, and in that case there may be phase delay, lead, lag, or anything in this reference, and instead of firing at the proper places, your switches will not be fired at those places, and you will not get the desired result. That's why these classical control techniques, which are based on some PLL, which are based on some transformations, they are nowadays they are becoming obsolete. But due to simplicity of these techniques, when suppose there are not great variations, much variations are occurring in the system. Suppose if you are getting constant wind energy throughout the 24 hours. These controls may be helpful because it is easy to implement. These controls can be operated with very low cost processors. Suppose STM32 or ARM Cortex. Any microcontroller can be used to operate these kind of controls, right? But suppose if we are using some costly controllers, then we can use some efficient control algorithms, and those efficient control algorithms are based on some intelligent principle, intelligence. It is not exactly the artificial intelligence, but intelligent control mechanisms are able to change their control parameters according to the changes from the input side. In this control algorithm, there is no change, though your input side may be changing, right? So these are some drawbacks of the classical control algorithm. Now we are moving towards the basic principle of the intelligent control algorithm. So this is the basic principle, Adeline principle. It is known as Adeline adaptive linear neuron principle, right? Because intelligent controller is based on the principle of Adeline, right? Adeline is very short form. Full form of Adeline is adaptive linear neuron. So this is one neuron we can say here, and this is getting the signals from different instants. This signal is sampled at nth, at x n minus 1th time, at x minus capital N plus 1 time, and basically these are the synaptic weights. Any neuron, if you study the basic structure of the neurons, they are synaptic weights. There are input, then synaptic weights, and then aggregator, and then that is activation function, right? Sigmoid functions are used for the activation purpose. We will take that also in this session. So xn is nothing but input quantity, and then these are sampled at different stages. And suppose xn is the nth weight, then omega 0 n, omega 1 n, and omega n minus 1 n, right? And we are taking this multiplied by xn multiplied by omega 0 n, xn minus 1 multiplied by this. This is the basic principle for any adaptive control algorithm. For any adaptive control algorithm, these are the three basic steps: filtering, error estimation, and tag weight vector adaptation. This adaptation algorithm, what is the meaning of adaptation algorithm? Suppose this is without any adaptation and this is with adaptation. What is the difference between this and this? There is no feedback. Whatever the signal you are getting as output signal and desired, difference becomes difference. But in this case, there is one feedback mechanism which is trying to minimize the error between the desired and what is you are getting actual, right? Actual and desired, this En is coming, and En is processed through some convergent principle, some convergence principle. And these convergent equations are based on least mean square principle, LMS. So LMS is changing these weights, and if weights are changing, your output Yn will change, because if weights are changing, they are multiplied by X. Suppose you are getting here, what you are getting here? X into xn into omega 0 n. What we are getting here? Xn minus 1 into omega 1. What we are getting at this place? This multiplied by this. Ultimately, if these are changes, we are getting different yn, and it may be closer to dn. That means error becomes, in the next iteration, error en becomes somewhat smaller. And again, if there is error, though it is very small, but it will be still not zero, then again it will be going into process, and then again these weights will be changes, and this process will continue till yn is not equals to dn. When yn is equals to dn, error becomes zero and weights will be, that means we will say yes, weights are now stable weights which are producing zero error. So this is the basic fundamental principle of any intelligent control. That means if we are changing, if error is coming from desired and actual, and if error is processed through changing the synaptic weights, ultimately what we are doing, we are making error zero, though changes are there in the system, right? Ultimately, there are three steps involved here: filtering, error estimation, tag weight vector adaptation. Yn is nothing but transpose omega n into x. This is nothing but sigma. Actually, here it is written for only nth instant, but In general, we can say it is I equals to 1 to n minus 1 and omega I n xi n, right? And because these two are column vectors, for multiplying column, both column vectors, we have to make one vector transpose. That's why this is omega transpose n into xn. And error estimation is en equals to dn minus yn, right? Error is nothing but desired and actual difference. And type weight vector adaptation, this is one convergent principle based on least mean square root principle, LMS principle, omega n plus 1. That means advanced stage weight equals to the previous weight plus twice mu. Mu is the learning rate actually of this adaptation process, and en is error, and x is the input, or we can say unit templates of the system. So this equation, how to utilize these three equations to form anything for the for getting the desired objectives of our system. Our system is microgrid system having wind and solar, or it may be based on only solar, or it may be based on only wind, or it may be combination of both, right? But similar control can be used unless and until you are not using more than one inverters, right? But how to utilize these three equations, how to utilize these three things in our system. Now this is one block diagram I have shown here. Now you can see these are the outer controllers. In the previous classical control algorithm, I told you about what is the significance of this, because we have to maintain anyhow, we have to maintain our DC link fix. That's why DC link reference is taken. DC link reference, suppose we are working on 230 volt AC system, we have to take DC reference 4 volt, 400 volt, and this is the actual DC reference and actual DC. Actual DC is sensed with the help of voltage sensors and other sensors. If you use in the simulation, directly you can take the DC value from there, and we can compare it. We are creating one error for the DC voltage, and this controller, this is DC bus PI controller, that will be maintaining VDC equals to VDC reference, right? So this is given over here. I will tell later on why it is given over here. Now you see, just first this equation, omega n plus 1 equals to omega n plus twice mu e n x n. People who are working in the research area, or if you are working with microgrid system, how to utilize the adaptive control mechanism, from these relations you can understand. It may be very helpful to you in simulation as well. And these are the simulation equations. We can make the blocks omega PA. Actually, there are 6, 1, 2, 3, 1, 2, 3. There are basically what in the classical control algorithm also we have seen decoupling of the components ID and IQ. Here also we are decoupling the components from the available currents ILA, ILB and ILC, right? From these three, we are calculating the active component of phase A, phase B, and phase C. And from these three, we are calculating the reactive component of phase A, phase B, and phase C. Now you see, this is the weight K minus 1. You can write here K plus 1, then it becomes K. That means this is the advanced stage, this is the just previous stage. Learning rate, eta, here it is taken as eta, learning rate. And basically the value of learning rate is changing from 0 to 1. It may be helpful to take 0.6, 0.7 for faster convergence. And then this is nothing but error. Error is IL, Y minus DN. Basically output is IL minus this, desired, or you can say actual current is ILA minus this is the X, right? Or you can say whatever you are getting D. You just see this equation YN. Error is nothing but DN minus YN, right? So what is here? IL minus W into UPAK. This is the error, right? UPA means X, and here also you are getting X. So entire equation becomes the convergence equation for the weight. And whatever the final weight is coming from this relation, because I told you it was the basic philosophy, this process will be going on, iterations will be going on, 3, 4, 5 up to 10, 100. Sometimes it may be taking more iterations, but ultimately it will stabilize all these weights to make the error 0. Similarly, here you will get the 0 error. You will get the 0 error when this weight equals to this weight. Finally, you will get one weight, that is WPA, right? And WP is multiplied by this. We will get some reference, because W is nothing but it will come in terms of DC weight. So DC weight multiplied by sinusoidal, it becomes I star SAPK. This is nothing but active component of phase A. Active component of phase A, this is equals to weight multiplied by the unit template, right? And we are getting here WPA. Final WPA will come and reference current will come. There are two things coming from this block: final WPA and then finally reference current, correct? And similarly, we will calculate from this relation the reference current active component from phase B for phase B and WPB. Similarly, for phase C, and all active components are added with the DC bus component, because this is nothing but DC bus component is nothing but whatever the switching losses occurring over the inverter, that must be added over here with the active component, because losses are the part of active power. That's why whatever the active power is required from the generator side, that must be added over here, right? And this is divided by 1 by 3 for making the balance over the phases. One ABC, we are dividing it 1 by 3 and ultimately getting giving the feedback, because again it is going into some convergence process. WPA, sorry, this is not given 1 by 3, but this WPA is giving feedback over here because it is participating in the next iteration. That's why this feedback is provided. Similarly, the reactive components we can see here 1 by 3, and this is minus, 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 and then plus. Plus is what? Computation of the voltage is done from this relation. VA, VB, VC, they are sense voltage from the supply side, and then computation of terminal voltage amplitude is coming. VT is nothing but under root 2 by 3 VSA square plus VSB square plus VSC square. These things are given in my paper, as well as the people who are working in this area, everywhere this can be seen. It is given widely in the literatures. Vt is equals to 2 by 3 under, first of all, under root, entire under root, then 2 by 3, inside the under root 2 by 3, VSA square plus VSB square plus VSC square. We are getting the amplitude at the PCC, and then this is the reference, right? Yesterday I told you how to set this reference. Suppose if you are working for 230 volt system, you have to take 230 by root 3 into root 2, right? Then you will get the amplitude over here, and whatever the error. Ultimately, what we want to do, we want to maintain the constant DC link, as well as we want to maintain the constant terminal voltage over the from where the loads and the grid is connected, right? That's why this is needed to make error 0. Voltage terminal is, that's why voltage terminal is processed through again PI controller. First of all, we are calculating the voltage terminal voltage, and then we are comparing with the reference, set reference of the terminal voltage, and ultimately PI's sensors, PI controllers are giving one vector that is equivalent to reactive power vector, and this reactive power and all the reactive components which are getting from the processing through the control algorithm, they must be added here, minus, 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 and then finally this component will be plus, right? And ultimately 1 by 3, this is again taking the average for making IA, IB, IC are equal, and finally you will get two components, you can say 3 components of the reactive, this ISAQ, ISBQ, ISCQ, because once weights are known, just multiply by the templates. Template calculation is done over here. You see these blocks. Template is calculated VA, VB, VC, and these are the unit templates of in phase, and these are the quadrature phase templates, right? They are calculated from these blocks. And how to calculate this? Again, this is the calculation of VT. VT is done from here, and ultimately UPI is what? Only sine omega t. UPV means what? Sine omega t minus 120. UPC means what? Sine omega t plus 120. Unit template means sinusoidal with unique magnitude. That is known as unit template. Right. And reactive template means they are 90-degree quadrature with these templates. There is one mathematical relations by which you can convert all the in-phase templates into quadrature phase templates. So basically, now we are adding all the active components and reactive components phase wise, and we are getting phase current, reference current for phase A, reference current for phase B, reference current for phase C, and we are measuring actual currents. And finally, using the control of PWM controller, pulse width modulation, in pulse width modulation, what is required? Modulating signal as well as carrier signal. The modulating signal you are getting just from the difference of this and this, reference and actual. That means error signal is working as a modulating signal over here. And we are taking 10 kilohertz or 5 kilohertz, carrier signal, right? Triangular wave or sawtooth and whatever carrier signal you can take. And finally, over the cutting points, we are getting the pulses. So things that means through proper using proper controller comparator, which will provide the instant of the that means either carrier signal is more than the that this signal modulating signal, then you will get the pulses. It depends on which kind of settlement you have done in the comparison block. Suppose, are you comparing greater or equals to, are you comparing less or equals to, right? So that is dependent on the comparator used for the pulse width modulation. So by this way, my basic is, by this way you will get the 6 pulses for the generator. How these 6 pulses are generated? So this is the entire philosophy, where we are calculating active weights, where we are calculating reactive weights. All the active weights are added, all the reactive weights are added. Then if solar component is there, solar must be subtracted from here so that you can get remaining active power from the other source. If it is only one base system, you can take only these only plus plus plus, and this DC link should be maintained by this path. Terminal voltage can be maintained by this controller. So these things are very much simple to understand. And how to calculate VT, what should be the value of reference over here, what should be the value of DC over here, what should be the value of DC reference. All these things are basic, and we must know how to uh, put in the simulation blocks. So by this way, we can create the signals. Now I'm taking another intelligent control mechanism, that is known as back propagation feed forward network controller. This is basically based on neural philosophy, where we are using 3 layers: input layer, hidden layer, and output layer. In previous one, any question, any query you can discuss. In this, if you have any query, you can discuss this. Okay. I'm moving towards the second one, that is based on the back propagation. In back propagation, how to design the control algorithm. So basically, back propagation is multi-layered feed-forward network consisting of input layer, hidden layer, and output layer. Input signals passes in feed-forward direction. That means the mechanism which is valid, which is applicable over the input level, the same mechanism is applicable over the hidden layer, and finally the same mechanism is applicable to the final layer. Suppose number of layers, if you are increasing, calculation will increase only, right? So things are very much transparent over here: input layer, hidden layer, and output layer. And you know, in each and every layer, there is one synoptic weight, there is one input signal. Input signal is always multiplied by the synoptic weight, right? And then after activation function, it becomes input signal for another layer. So the same thing we are applying over here. you can see here ILA, ILB, ILC, these are the basic inputs and these are the templates, right? And these inputs are working as a synoptic weights with these templates, right? And omega is nothing but initial weight of the synoptic, that means synoptic layer. So we are getting two things, ILPA and ILQB. That means actually this should be QA instead of B. It should be QA, ILPA and ILQA. And by using this relation, we are getting this, and this is the basically output from the first input layer, right? And after applying the sigmoid function, that is activation function, sigmoid function is used, sigmoid relation is here, and after the application of the sigmoid functions, we can get XPA. XPA equals to 1 upon this plus. If you plot this, you will get some kind of sigmoid functions, 1 upon 1 plus e raised minus x, right? Instead of x, we are getting the input for this activation block is ILPA and ILQB. What I told, the basic philosophy is input, then synoptic weight, and then you are getting one intermediate output, and that intermediate output you are giving to the uh, input at the activation function, and finally you are getting output of the neuron, right? So this is nothing but output of the neuron. XPA equals to 1 upon this and XQA is this. And now it is going to be applied over the second layer. The same equation what we have done in the previous one, the similar steps are just organized over here. WN plus WPA, XPA plus PB, XPB plus this. Whatever the things you are getting here, these are useful. These are used as an input for the second layer where synoptic weights are given like PA, PB, PC, QA, QB, QC, right? This is one neural philosophy based network and neural based control algorithm. That's why, because continuously these are changing and they can adjust much faster. That's why we are using it. And it becomes IPA and IQAL, right? And XPA, XPB, XPC, these are the output of the sigmoid function, activation function, right? And these are the initial weights. These are the initial weights. These weights can be adjusted with the help of these two relations, right? This is nothing but what I told you about the least mean square principle, where learning rate is defined, where error is coming, and finally multiplied by the input weight, right? So this is the input weight XPA, XQA, and this is the error actually, and this is the learning rate, and this is the previous WPTR and WPAR, right? Finally, you will get the WPA and WQA from entire neural network. And again, they will be activated. Final layer will be again activation function will be implemented. You will get PAL, QL from each phases. And finally, all phases will be added and divided by 3. We will get WPT and we will get WQT. And the things are given here, the same philosophy. Suppose the similar blocks are used, but here ILQ and IPBL. How to correlate these things? Already we have discussed through these mathematical relations. Finally, you will get these things because instead of using 6 blocks, we are using only 3 blocks, and active reactive calculations are done in phase wise, right? This is for phase A, phase B, and phase C. And finally, we will get 2 quantities, active and reactive, active and reactive, active and reactive from all the phases. And by adding all these 3 and divided by 3, we are using LPF for suppose 10 or 20 radian per second. And then we will get WPT, WQT by multiplying some gain coefficients and adding and subtracting with the DC-link components here, and DC-link components, this path, reactive path. Finally, you are getting WPS and WQS, and then multiplied by UPA, UPB. Suppose if you are multiplying WPS into UPA, we will get the phase of active phase of phase A active phase of phase B, active phase of phase C. And this is multiplied by this reactive phase of phase A, reactive phase reference of phase B, reactive reference phase of phase C, and then added all. Actually, some intermediate steps are not shown here, but you can understand for calculation of phase reference A, active and reactive must be added. For B, active reactive must be added. For C also, active reactive must be added. So from where you are coming, you are getting active and reactive. This multiplied by this multiplied by this multiplied by this, you are getting all the phase components of active component. And similarly, QS multiplied by QA, QS multiplied by QB, QS multiplied by QC. 3 reactive components phase-wise will be created from here. And all the active phases components over here and here, they will be added together. Suppose phase A active, phase A reactive, phase B active, phase B reactive, phase C active, phase C reactive. They will be added, then you will get ISA star, ISB star, and ISC star. ISA, ISB, ISC, these are the actual supply current sensed, and we are getting one error modulating signal. And signal is again compared and with some PWM techniques. We all know PWM techniques based on that means carrier signal, modulating signal, and comparator, right? These 3 things will be involved over here, and finally we will get the 6 pulses for the our inverter. So this is one another control, intelligent control, where weights are adjusted according to the system need. Now this is another control based on LMS based principle, and it is little bit mathematics, but very much useful. The people who are working in this area and the people who wants to use some adaptive controllers for their use, right? If you are a researcher, you can use these controllers either in any system. Multiple sources can be interfaced with one inverter, right? Just you have to define your topology first. Suppose yesterday we have discussed a lot of about the topologies, how we can change the topology, how we can minimize the number of inverters in the topology. Suppose if somebody is using 3-4 inverters are necessary, you have to design 3-4 independent controls, because basically we are working over here at the primary level control, device level control. And if your number of devices are increasing, independent controls will be increasing. The similar control can be designed for 3-4 inverters, and then ultimately they must be running simultaneously in the controller. Then your cost of the controller will increase, because normal controllers cannot handle 3-4 control mechanisms at the same time. Then you have to go for some costly controllers like microlab box or D-space, or some high cost, high frequency processors, right? Where 3-4-5 control mechanisms. Suppose if I say a microlab box that is costing almost 16 lakhs, you can run 4-5 mechanisms together. These things are very much important to learn. And now this is another control, that is momentum least mean square control. That is the category of adaptive controller. And the inputs are the same, like just we have arranged 6 equations. 3 equations are used for active power control, 3 equations are used for reactive power controls. Right, and ZPK plus 1 equals to ZPK. Z is nothing but weight, and this is a very simple equation actually. If you understand the third term is nothing but momentum term. Otherwise, if you see the first term and second term, it is very similar to the terms which are used in the first neural network. But in this third term, what we are doing, we are just utilizing the concept of NR method. In NR method in power system, somebody may be knowing the NR method. NR method concepts are utilized over here for making the momentum term, and by utilizing this momentum term, we are getting the very fast response or very fast convergence process. Actually, this is designed by me during my own PhD, and we have published the paper in IEEE Transactions of Industrial Electronics. And this paper, there was one question when it was going under review process. They were just asking like, what is the new in this thing? Then I given one comparative results without this term and this term. Then immediately they accepted my argument, and they accepted the paper as well. So the things are very much clear from this relation. This is the extra term known as momentum term. It is creating a big difference in the speed of the control, because everything is accelerated by using this term, right? So entire philosophy remains same. Only thing is this terminology and this term. Otherwise, things are remains same as we have discussed earlier. This is another neural philosophy based neural network based RBF, radial basis function control, and the equations are a little bit different, but only thing is ultimately we are getting the WP and WQ, and phase wise we are getting the normalization. Only thing is 1 by 3 we are doing. We are adding all the weights. We are giving 1 by 3 and using LPF, and all these things are remain same whatever we have discussed earlier. The only thing is equations. Equation is based on radial basis function. The people who are aware about the neural philosophy, they may be knowing these terms: neural network based, RBF based neural network. And these are some simulation results. After implementing the control into the MATLAB, we have got some simulation results when we are changing the wind speed, and we are changing the variable load, when we are varying the parameters of the, I have shown the results in the simulation when only wind is taken into consideration, and then finally when wind and solar both into consideration. So here in this, we are taking the load non-linear. You can see the shape of the load current. This is totally looking non-linear load, right? And transient is created at 7.5. You can see the difference of the wave shape. Up to the 7.5, entire thing is coming. All phases are coming. And after this, only two phases are running. One phase is disconnected, just for creating the unbalance in the loading condition. But what is our objective? Though the loading conditions are unbalanced, but from our topology, generator current must be balanced. So we are looking here from 7.5 onwards, load current is unbalanced, but generator current is balanced. All phases are getting the currents, and they are almost equal in magnitude. And similarly, we are getting the terminal voltage, because our load is connected in all topologies what we have discussed. Actually, in either it is solar rooftop panel or it is the wind hybrid mix combination, your ultimate terminal voltage is in AC, right? Because loads are connected from the AC microgrid. That's why voltage must be maintained over there. Otherwise, entire loading system will be affected, right? If load variation, if voltage fluctuations are there according to the input output variations, that is not the desired objective. The desired objective is whatever the variations occurring from the load side, either from the load side or from the supply side, but your terminal voltage must be maintained. And from this simulation results, you can see despite the transient after 7.5 onwards, we are getting the balance voltage, balance current, right? And similarly, we have maintained the zero sequence current, zero from the generator side. That is also one objective. Yesterday, I told you about the various objectives of standalone systems. The load balancing must be there. That means your inverter must supply balance current in each phases, IA, IB, and IC. And inverter must maintain zero sequence current from the supply side, zero sequence. That means zero sequence current must be zero from the supply system, though it may be there in the load side, right? So these things we can observe from the results. This is the compensator current. Compensator current can be seen some settling points. It is supplying the harmonics. Compensator is supplying the harmonics. That's why your supply becomes non-harmonical supply. That means it becomes purely sinusoidal, because harmonics are taken care by the compensator itself. VB battery voltage we are using, as I told you, battery is the integral part of the standalone system, right? That's why you have to maintain the battery supply constant, terminal voltage constant, And frequency is one very important component. You can see here, frequency is almost maintained constant during the transient condition. Transient is created at 7.5. Frequency is going somewhat upper because you are decreasing the load. If we are decreasing the load on the system, frequency will go up, but it is controlled by using the controller. We are using frequency control loop in the controller, and that controller is trying to maintain the frequency within limit. Within 1 or 2 cycles, frequency is again maintained at 50 level, right? Then this is the battery charging current. According to the loading disturbance, battery either discharge or charge, and things are shown here. You can see this is the fixed loading condition with variable speed. We can see here the changes from the wind speed occurs from here, and we can see the results. Loads are constant over there, but again, voltage and current, they are maintained sinusoidal, and they are maintained throughout, right? Only current is increasing because entire power system, entire power is increasing, right? And these are the some harmonic spectrum. We can see here the load current waveform that is showing 32.25% distortion level, but we are maintaining supply current 3.54. As per IEEE standard, 5% is allowed, but here we are getting less than 5%, right? That's why acceptable. So this is our objective was to maintain the sinusoidal supply from the supply system. And these are some simulation results based on microgrid system, solar wind based DG, where load rejection we have studied what will happen in load rejection, what will happen in the load rejection over the different parameters of these controls. These results are based on some different control because it is still under publication. That's why I'm not showing. There are some limitations from my side. I am not showing the exact control from where we have received the result. I'm not describing the control steps, but just I am giving out output of the control. And you will get the idea which kind of results are needed. And then this is load rejection. You can see the VT, terminal voltage. Terminal voltage is maintained over here, though load rejection is given. That means transient is introduced over 2.8, but your VT is maintained within few cycles after load rejection, right? Similarly, these are the templates what we are using in the control algorithm, UPA and UQA, right? And these are the some components of phase estimation and all during the grid disturbance. And this is the performance of the islanded microgrid during variations in the wind velocity, right? Change in the wind velocity, and we have recorded the variations of phase voltage, grid voltage, and ILA, ICABC frequency. Frequency is maintained around 50 hertz, and wind is changed over here, but still we can see the voltage profile is maintained. These are the solar irradiation variations. Suppose change in insolation level from 900 to 600, change in temperature, reduction in the PV current due to change in the temperature and insolation. PV current is reduced, and reduction in the PV power as well. But ultimately, what we are doing here, we are maintaining the voltage at the connection level, and then this is the grid current. We are maintaining sinusoidal, though load is totally non-linear. This is the non-linearity in the load. You can see that transients are introduced. Load is in some phases load is not there. And what are the various effects over the charging of the battery? Because battery is the integral part, as I told you so many times, in the solar wind system. Battery charging is started when we are reducing the load. The power which is generated from the solar and wind, that is going to charge the battery. That's why battery current is increases. And these are another load rejection, and we can see the various effects from the wind. This is the wind and solar interconnected system. We are changing solar insolation, we are changing wind just by one. We are not changing both, because during simulation you can understand what kind of complexity will be created if we are changing a lot of things together. That's why we are connecting system, but changes are observed one by one. Sometimes we are changing the insulation level of the solar, sometimes we are changing the wind velocity, and we are observing other things, right? So these things are is still under publication. This is my limitation. That's why I cannot show very much this. And then finally, we have compared 3-4 control algorithms: DTO, GIPLL, and ADF, FLL base, TOGI, PLL base, and LMS base. And we can see the transient performance of all these control mechanism. You can see in this result. And we can see here the power generation and the dynamics of the load and battery. If we are changing the PL and PV, this is the result when you can connect wind and solar at same DC link. That means PG is same from that place. And we are changing the PL, and we want to see how PB is responding. That means battery power. That battery, what is the use of battery? Battery is trying to maintain the fluctuations in the load, and you just see the dynamics of the battery under load fluctuations. Load battery is trying to match the load fluctuations, right? So these things are very much clear. Again, some spectrum is plotted over here where 30.55% distortion is created from the load side. Still, we are able to maintain through using control mechanisms 2.2%, 4.82%, like this. And again, we have used some another adaptive controllers. Suppose there are 5 control mechanisms are used here: AVF, MLMS. I explained the mathematical steps of the momentum least mean square, then Lorentzian adaptive filter, then VCOLS PLL, and then non-linear adaptive Volterra filters. There are 5 control algorithm comparison is given here. During MATLAB simulation, it is found that the variations in the voltage and frequency, this is the voltage variations at the terminal, and this is the frequency variations at the terminal. And just from this, I want to just give one conclusion from this one. We cannot say the control without implementation, it is better or not better. Right, after implementation, we can say yes, in this particular condition, in this particular situation, which control is performing much better, right? And the dependency on the parameter selections as well, it is defining the efficiency of the control mechanism. So there are so many parameters, so there are so many things into consideration for deciding the entire performance of the adaptive controllers, how adaptive controllers are functioning in different operating conditions. So from this one, we have implemented in the similar conditions, we have implemented 4 control algorithms, 5 control algorithms in fact. And these control algorithms, the best one performing control algorithm is AVF. AVF is giving minimum error in the steady state after settling, and in the frequency as well, AVF is performing much better. From these 5 controllers, adaptive voltage vectorial filter is giving a very nice operation and function. And the functioning of entire control algorithm is just summarized over here. This is also one important parameter. What is the sampling time required? Because you see, if control algorithm is taking much more sampling time, and it depends on the complexity of the control, right? Suppose 120 microsecond is taken by NAVF, and this is taken by DSpace 1104. Actually, I was implementing the things on DSpace 1104. So just you see what will happen if you are using low cost processors like STM32 and all, right? Now, this was the part of simulation. Now I am going to give some clue about how to develop the DG prototype. If you have any query, you can ask this. Design and development for DG prototype. Suppose whatever the system you want to simulate, finally you have to design it and you have to develop for the prototype as well. If you want to develop your system fully, experimentation is very much important. Basically, here I will discuss the things which I have developed in my laboratory. I am skipping the design steps because there are there are so many things involved, but most of the things you are already knowing how to design, and it will take some time. How to design the converter, how to design the battery backup, how to design the generator, how to design the solar plants, how to design everything you are knowing already. And the components are involved for this design. Suppose wind system is emulated by using motor generator. This is the D space. The characteristic of the D space is 8 ADCs and 8 DACs are used over here. Out of 8 ADCs, 4 are mixed in nature. That means 4 are they are taking 4 signals and giving one output, right? Things are given over here, and the important thing is these ADCs are converging signals in both directions, right? Conversion is possible in both directions. Sinusoidal signal can be directly converted into digital signal by using this. But in microcontroller or STM32 or ARM Cortex, you have to set one offset. That means if you want to sample the signal, sinusoidal signal, you have to raise sinusoidal signal beyond the x-axis. That is offset. You have to provide the offset. And after sampling again, you have to in the software, that means in the program, you have to take minus of all those samples, right? So this is one approximation you are doing in the low cost processors. But in D space, sampling is possible in both directions. There is no offset required. These are the bipolar ADCs, right? And this is the inverter unit. You can design your own inverter, but what I used, I have taken the inverters made by Semicron. All the devices are kept over here. One fan is there, and these are the gate pulses. Yesterday I was discussing some optocoupler circuit. Somebody has asked me one question, how to raise 5 volt towards 15 volt, because IGBTs are fired at 15.6 volt. How to raise the signals? So by using optocoupler circuit, you can raise the voltage level from 5 volt input to 15 volt output. This is the battery block. These are the excitation capacitors. So all these components, and then design of the voltage sensors are needed. According to the data sheet, you have to go for what should be the limit of this current, what should be the limit of this voltage. According to the data sheet, you have to design the voltage sensor, right? Similarly, design of the current sensor, because in hardware experimentation, sensor design is very crucial. If your sensors are not efficient, if your sensors are not giving the good result, nothing will come from the hardware. That's why sensors are integral component, or you can say there should not be any lag from the sensor. There should not be any phase angle error from the sensor. Whatever the signal at the input of the sensor, less amplitude signal must be the same phase. That means conversion should only play their role. Other things should be totally nullified. If you are getting delayed signals from the sensor output, there is no meaning. Nothing will be coming from your hardware. So these sensors I have designed, and steps are provided here. And then isolation circuit design is important, as I was telling. Here you are getting only 5 volt, and you have to make different DC supply from different grounds. G and D are, that's why I have written here G and D capital and G and D small. G and D, it is different ground provided from different battery supply, and this is the ground provided from different supply. And ultimately you are getting 15 volt across VU, and this is going to fed the IGBT driver. So these circuits, once you are working in this zone, then and only then you will get to understand how these circuits are working. Otherwise, things are just irrelevant for. And these are some experimental results. Only one results I would like to show here. Just you see load rejection. We have removed the load from here, but still we are getting the supply sinusoidal from the phases, right? And we are getting the compensator current and ISA. They are in same phase after load rejection. Battery voltage, similar voltage is coming after the load removal. So these are the some battery charging discharging characteristics, and when load is removed or load is added, we are getting the battery dynamics from here, how our base energy battery energy system is working, because it is supposed to supply under overloaded condition, and it is supposed to take the power from the system under underloaded conditions. So both are seen over here, and these results are already published in some transaction papers. And this is the neutral current compensation we can see here. and ISA, ISB, IC from the supply system. These are balanced and these are harmonic free, purely sinusoidal supply. You can see here the load current is non-sinusoidal, but supply system is giving you the sinusoidal supply current. These variations are measured from the input supply, input transients. Suppose mechanical power is not uniform from, but we are getting the uniform voltage profile from the terminal voltage. And these are some steady state results. We have seen the powers, active component, reactive component, frequency. We have captured these results by using power quality analyzers. And these things are references. And thank you very much. Hello. Hello. Am I audible?
Yes, sir. Yes.
Madam, if any query from the participant side, we can discuss.
Yes, I will check, sir. Chat box. No, sir. Any query from participant? If you want, raise your hand. I will unmute you. Please, participants, if you have any query, please raise your hand.
Actually, today was very busy day for me here also. That's why it was. Otherwise, I could have taken 30 minutes more.
Sir, please continue. There is no query from the participants.
Okay, if some participants, if they are interested to work in this zone, if they want to interested to work, or if you want to take some guidance, I am ready to help them. And you can share my mobile number as well as my email ID with all participants. And currently I am working on solar microgrid, solar and wind microgrid system. We have done a lot of simulations in this area, and we are developing experimental setup also. And if you are interested to take or to collaborate with me for any work, you can collaborate. I will be happy to help for collaboration as well. So this is all about from my side. Thank you very much for inviting me and for giving me this opportunity to present my work. Thank you very much, madam.
Thank you very much, sir. And thank you very much all the participants who have continuously present here and listened very patiently to our experts. Thank you very much, sir, once again for giving your precious time. And if any query, any participant want, then they will ask or send me message on my number.
Yes,
okay.
yes.
One person
You
is
can
asking for
share.
a contact number, then I will share your details with you.
Yes, you can share my number.
Okay, Singh Amit, I will share the contact number and details of the expert with you. Okay, anyone, any else? Vishal says, thank you, sir. Thank you, Vishal. Mr. Arun Hanuman also says, thank you, sir. Thank you, behalf of all the participants.
They are not asking any question, just they are giving me thank you, thank you.
If after just going to this session, if any query, you can ask. We have the expert till tomorrow. Sir will definitely give the answer your question, if any. Okay, sir. Then thank you once again.
Thank you, madam. May I leave now?
Yes, sir. Thank you.
Thank you very much, madam. Thank you.
Bridget, sir, please stop our sessions live telecast.